This is a clip of it in your notebook, but I would write a lot of this information down actually in your real table R reference table. So here we go. We are going to start adding things to those parent chains and replacing hydrogens with some other structures. You will need to be able to classify the type of organic structure. So the functional group, what we put on that parent chain, changes it from a simple hydrocarbon to something else. So you're going to have to be able to recognize these. You'll need to be able to circle or underline the functional group. You have general representations, and you'll need to be able to add them. If you use your table R, there are lots of hints here of how to handle this. Okay, so a halide or a halocarbon, well, it's because we have an atom from a group 17. So this is where we add a group 17 atom to the parent chain. And it's pretty simple here to recognize. Chlorine's probably the sneakiest one, so we can see it right there. And so we have an example here of the name. So we have propane, where we have a 3-carbon parent chain, single bonds, and we have a chloro attached to it. So chloro is the abbreviation for the chlorine, making it a halocarbon. Okay? Now, alcohol. Lots of stuff on alcohols. So alcohol is a classification. There are many different types of alcohols out there. So alcohol, it ends in OL. An organic structure belongs to in the alcohol family if you notice that the ending is also OL. What we replace a hydrogen with is this OH group, and R just represents the parent chain. And that tells you somewhere on your reference table. So R is the parent chain. And a lot of times we're only interested in that segment of the parent chain that we have a functional group attached to it. So we attach an OH to the parent chain. The oxygen is attached to the carbon on the parent chain, not the hydrogen. And here's the thing. So what I want you to learn to look for is a sequence of letters. So most of your organics are going to be some sort of combination of carbon, hydrogen, and oxygen. So we look for letter sequences, not subscripts. So whenever I see a sequence of HOH, okay, I recognize that in the structural formula as being an alcohol. And a lot of years ago, in my organic chemistry professor said this, and I never forgot it, is that some people drink alcohol like water. So if you see a sequence of HOH somewhere within the structure, you have an alcohol. Okay, so now moving on to the ether. Here we have an oxygen bridge. So this is a bridge. And you will see that it is a bridge linking two different parent chains. Now, this is how you remember it. So to recognize that this is not an alcohol, because you notice there's no HOH. I see HOC, but there's no HOH in this one, right? But who visits you in the springtime? So here we go. The ether bunny brings you chocolate. So when you're looking at the sequence where you see chocolate in the formula, CHOC, you know that the ether bunny has brought you a treat. And these parent chains are kind of like the ether bunny ears. So here you have your ether bunny. So the O is like the ether bunny's face, and the two parent chains that links together are like the ears. Okay, so aldehydes. So aldehydes start with AL, and if your name ends in AL, you're going to see aldehydes. Now, here is the aldehyde functional group. This is a partial structure one. what you are going to see in a fully condensed one is CHO. So to the right terminal, if you see CHO, you've got an aldehyde. And so aldehyde, this functional group is terminal. And terminal ends in AL. Okay? The next one is a ketone. So notice it's -one, like acetone, ketone. So if your name ends in, I know it looks like one, but it's -one. So you're looking at that chemical name, it ends in ONE, you should recognize it as a ketone. And so here is the functional group for the ketone. And what you are going to see if this is fully condensed, the letter sequence is going to be COC is what you're going to look for. And the O, it gets attached to the carbon with a double bond just before. So the ketone is somewhere on the interior part of the chain. Okay? So now we have organic acids. Take a look. We have oic and acid. So big clue, it's an acid because the molecule name has the term acid in it. It's an organic acid if it's oic, organic acid. So ic is a very common ending for an acid, but it has that O in there. It is oic acid, so organic acid. So the functional group is this guy. And in a condensed, fully condensed that you will see it as, you are going to see it as COOH for an organic acid. All right. So now, here we go. Now we have ester. So this is grandma. So this is grandma ester. Ester's kind of an old-fashioned name, so grandma ester. And here is the functional group. But the way that you're going to recognize it in a fully condensed is grandma ester is a great cook. So you're going to see COOC. So you see cook in the structure, you've got grandma ester. And because grandma ester is a great cook, esters are known for their good smells. Now, the amine and the amide, you might need to classify one. We won't be really drawing these or naming these, but just pay attention. So we have the name amine, and take a look. It says amine in there. And take a look. An amine, okay, it's built around nitrogen with carbon chains attached to it. So you're just going to look for a nitrogen in the structure. Now the amide, pay attention to details. It has a similar name, but if you're asked to, you're given some random organic name and you see it ends in amide, you should be able to classify right away that it's an amide. And amide, I know, sounds a lot like amine, and that's because both have nitrogen in them. But take a look at the difference. The difference is that you will still have the nitrogen, but you will also have the oxygen. We won't be drawing or naming, but you may need to classify. Like you might be given a structure of an amine or amide and need to classify it. So just know what to look for. Use your table R.